Picture the universe as a cosmic kitchen where stars are born from clouds of gas and dust. Around these newborn stars, spinning disks of leftover material, protoplanetary disks, form the ingredients for new worlds. These disks are filled with gases, dust, and ices, the building blocks of planets. In the cold outer regions, water exists as ice, coating dust grains and making them sticky. These icy pebbles clump together, growing larger and drifting inward toward the star. As they approach the warmth, the ice turns to water vapor, enriching the inner disk where rocky planets like Earth form. This process, we believed, delivered water to young planets, setting the stage for oceans and life. Our solar system seemed to follow this recipe, with comets and meteorites as evidence of ancient water delivery. For decades, astronomers expected to see this same story in other star systems. We searched for water vapor in planet-forming disks, confident that water-rich worlds were common. This neat explanation shaped our search for life beyond Earth. But the universe, as always, had a surprise waiting for us. Everything we thought we knew was about to be challenged. Enter the James Webb Space Telescope, peering into the star-forming region NGC 6357. Scientists focused on a young star, XUE-10, surrounded by a planet-forming disk. But instead of water vapor, they found the inner disk saturated with carbon dioxide. Water was nearly absent, completely upending expectations. This discovery sent shockwaves through astronomy, challenging the standard model of planet formation. The data showed a chemical environment unlike any we'd imagined for rocky planet birth. If a planet formed here, it would be born from CO₂-rich material, not water. Most stars, including our Sun, are born in crowded clusters like NGC 6357, not in isolation. So water-poor disks like XUE-10s might be common, making our water-rich solar system the exception. This single observation opened a new chapter in our understanding of planetary systems. What caused this dramatic shift? The answer: intense ultraviolet radiation from massive neighboring stars. This UV light bombards the disk, breaking apart water molecules before they can reach the inner regions. The lighter hydrogen and oxygen are blown away, stripping the disk of water. Carbon dioxide, being more robust, survives the radiation and dominates the inner disk. The JWST even detected rare isotope hologs, unique forms of CO₂, offering chemical fingerprints of the disk's history. These findings may help explain the unusual isotopic patterns in comets and meteorites in our own solar system. The local environment, it turns out, can drastically alter the chemical building blocks of planets. A quiet, isolated star system might be water-rich. A crowded, high-radiation cluster could produce dry, CO₂-dominated worlds. Planet formation isn't a universal script. It's a collection of stories shaped by each stellar neighborhood. The diversity of planetary systems is far greater than we ever imagined. The universe is rewriting the recipe for making worlds. This discovery expands our view of planetary diversity. For years we searched for life by following the water, but XUE-10's disk suggests some planets may form nearly dry, with thick CO₂ atmospheres. Such worlds would resemble Venus, scorching and inhospitable. A recent JWST observation of a CO₂-rich water-poor comet hints these systems are not rare. That comet may have originated in a high-radiation environment like XUE-10's. Understanding this diversity is crucial for our search for life. It reminds us that Earth-like planets may be rarer than we thought. The history and birthplace of a planet shape its fate and habitability. The James Webb Space Telescope is revealing not just what the universe looks like, but how it works. The cosmos is more complex than we ever imagined, and our journey of discovery is just beginning.